So good morning to everyone. Nice to see all of you here after yesterday, and since this is the last day, so thank you very much for coming. This morning I'm going to talk about the Oracle demo plant that is the ISRU technological demonstrator that the Italian Space Agency is developing together with the Polytechnic of Milan to extract oxygen from lunar regolith. So, okay, I know the picture does not look good, but I hope you can see it on the screens. This is a very, very quick overview of the whole system. Basically, we have the orange part here, which is the core system, in which we have the main reactor where the process takes place. The process is based on a carbothermal reduction in which methane is used as a reactant to extract the oxygen from the lunar regolith and convert and produce carbon oxides here. So this is the main main component that we have. And however, we would like to develop a baseline configuration in which also we have a second reactor here in which carbon oxides are converted into water vapor, and later through a condenser, liquid water is obtained. As you can see, actually, we have also a blue box here, since in an extended configuration, which is not very clear here, but we may have to develop also a regolith loading mechanism, but I'm going to go and touch this point a little bit later. Anyway, this whole system is supposed to be sent to the moon through let's say, either a commercial launch, or we are evaluating the possibilities, and also this point is going to be one of the points I'm going to talk about later. Anyway, so this was the ELS of last year for those of you who participated, and the project had not been started yet. So it was June 2023, and right now, a year later, according to the schedule that I presented last year, we are actually on time, since the project, the studies phase AB1 with the university is actually going pretty well. We had the kickoff last year in July. We also performed the first technical review in January, and we are approaching the PRR late this July. Regarding the industrial partner, we are selecting the partnership, and we hope to start the contract by after the summer. Instead, let's say the most critical, but the part that we are evaluating right now is the transfer launch and transfer service, in which we are evaluating the different possibilities according to the providers that we are talking to. The whole project is funded beside launch, and we are targeting 2028, 2029, let's say the 2028 timeframe for the launch, with operativity in the, let's say, 2029, more or less. So going to how we managed to, what we are targeting to develop. This is a, let's say, mass budget configuration trade-off that we performed to evaluate the size of what we want to develop. Okay, the colors are not very clear here, but as you can see, the carbothermal reactors, so the orange one is the subsystem that is heavier among the others. The configuration that we chose was, as I said at the beginning, the one comprehending all the subsystems in order to obtain liquid water. So including the methanator and the water extraction unit, but excluding the regolith loading mechanism. And I'm going to say it why in the next slide. We want to process 30 grams of lunar regolith for 10 hours in order to maximize the yield of extraction of the process, while keeping the whole payload below 15 kilograms. And we would like to repeat this process 2 times, while the third cycle would be, let's say, best case. Also, according to this table here, we add a trade-off in which we could decide if releasing the exhaust regolith in the outside or keeping it into the reactor. We chose for the stacked configuration in order to keep the system more simpler, while also make the previous batch participate in the reaction process. So regarding the regolith loading mechanism, this is a point that is very, let's say, critical for the process, not for the subsystem itself, but because of its relevance. We need something to pour regolith into the reactor, otherwise we cannot perform basically anything. So different options are under evaluation. Of course, if we are on the lander deck, either the lander has its own robotic arm, let's say, to collect the regolith from the lunar soil. Although this is a viable solution, not the preferred one because of some plume impingement effects that could, make the regolith contaminated. So the best case would be if either the payload were on a rover, or if a rover could go and be deployed to collect the regolith from far away from the landing site, or if there could be also sharing of the regolith loading mechanism with other payloads on board the lander or on the rover, such that some beneficiation analysis could be performed in order to measure either the mass or the composition or the granulometry, and relate those results with the yield of extraction at the end of the process. Of course, if none of this is going to be performed, we have somehow to provide the regolith loading mechanism on our own. So the first option would be to develop this internally as part of the Oracle configuration. Of course, this is not something we would like, since it will, let's say, take some mass from the other subsystems, so we are careful in evaluating these. Anyway, some activities are already on, let's say, in developing with the technology office at the agency. Otherwise, we are also evaluating the possibility of putting Oracle on the ground and make the collection by ourselves using a drill or a hoover. Regarding the interfaces with the provider, we also have the one related to the power management. Okay, so this picture is basically white. Anyway, as I said at the beginning, two cycle fresh regolith in 10 hours is our minimum threshold for the success of the mission. The best case would be repeating it 3 times using pristine regolith with variable composition. Here I mean that the rover, for example, could be in different landing spots and collect some regolith in different spots, and to repeat the process for 10 hours of continuous power process. This is because maybe it's not clear here, but this white area, which should have been light green, is the heating time, while the dark green area is the process time, and together they last for about 22 hours, in which we require, in a margined power scenario, 140 watts. So this is quite a lot for some providers. For this reason, we are evaluating different strategies to decrease this value, which would be for the heating phase to pass from, let's say, heating step from 4 Celsius degrees per minute to 2 Celsius degrees per minute. In this way, we would maintain the heating time below the 10 hours, let's say, while asking for less power. Regarding the power, the process phase instead, we may proceed with power width modulation, in which we have an average power less than the maximum one we had before, which here is not, let's say, margin, but if margin was about 80 watts, while keeping an average value of power minor. Regarding the accommodation on the lander, of course, I said before, it is related also related to the regulated loading mechanism, but also to the volume, which we would like to keep it below this value here, just for giving an envelope. Below 15 kilograms, in which we understand 20 kilograms could be our worst case scenario. But more importantly, the carbothermal reactor and the water extraction unit should not be exposed to direct sunlight due to their thermal environment. The carbothermal reactor should be such that its inlet is accessible for regolith feeding. Another important fact is that another important, let's say, interface is that we will release all the exhaust, so CH4 and H2, which are used in the process in the outside. So no other payloads that could suffer from the presence of these exhaust gases should be nearby Oracle, or let's say we should be placed in a way such that we do not harm any of these. So to conclude, this is a very important project for the Italian Space Agency, and this is, let's say, a process which makes us agnostic to the landing site, because the use of CH4 allow us to make the regolith react with any, sorry, to make the methane react with any regolith, the composition of any regolith. We do not foresee any programmatical aspect. We are soon selecting the industrial contractor, and we know the launch will be, let's say, we hope the launch will be in 2028 with a prior delivery of the flight model 6 to 9 months prior to the landing. Of course, as I said before, and I'm repeating it, the regolith loading mechanism for now is our, let's say, critical aspects that we are evaluating. Thank you very much for the attention.
Thank you, Francesco. Any questions from the audience? Oh, would you like to go first?
Did you look into recycling any of the excess gases that you're releasing?
Yeah, that's a nice question. Thank you. Yes, also because CH4 is also a product of the reaction at the end. But since we want just to, let's say, test and demonstrate the process for now, we are not, let's say, interested in putting extra mass for the or recycling of the gases. Anyway, if somehow we see that is a viable solution, we maybe do that too. But for now, it's not on the table.
Hi, Carl Hibbets, APL and part of the Lunar Surface Innovation Initiative. This is pretty mature technology overall, carbothermal reaction, but scalability is always an issue. What do you see as your largest challenges in scaling up from extracting O2 from 30 grams to, say, 10 to 100 metric tons per year?
This is a very nice question, actually. We have a plant at the Politecnico Milan, and right now they managed to process say more than 30 grams per batch. So of course, for now we just want to develop the technological demonstrator to demonstrate the feasibility of the process on the lunar surface in a lunar environment using real lunar regolith. If the process actually demonstrates itself, we may increase the size of each component. For sure, the reactor itself maybe is the most let's say critical one, just because of its importance in the whole process. But let's say we are facing the design. We will face the design when the industrial partner joins. We'll see what the problems are when it comes, and then we may be deciding what to do in the later phase.